Hello everyone, welcome to today's presentation. I'm excited to introduce our topic, motion in a straight line. This will be a fascinating journey into understanding how objects move along a straight path. We'll cover the fundamental concepts, equations, and real-world applications. So let's get started and explore the basics of motion in a straight line together. Let's explore the fascinating world of motion today. We start with the basics, scalars and vectors, which are fundamental to understanding any movement. Then, we move into the concept of distance and displacement, helping us distinguish between how far something travels and the change in its position. Next, we'll look at speed and velocity, emphasizing how quickly and in what direction an object moves. We'll also cover instantaneous velocity, which tells us how fast something is moving at a specific moment. Then, we delve into uniform motion, where speed stays constant, and non-uniform motion, where it varies. From there, we examine different types of acceleration, including uniform and non-uniform acceleration, to understand how objects speed up or slow down. The core of our discussion involves the equations of motion, starting with the first, second, and third equations, and how calculus helps us derive and interpret these formulas through derivatives and integrals. We'll see how these mathematical tools clarify the concepts of velocity and acceleration. Moving further, we'll explore velocity time and distance time graphs, which visually represent motion and help analyze different scenarios. Relative velocity introduces how the motion of one object appears from another's frame of reference, a crucial idea in understanding real-world interactions. We'll look at motion with acceleration, including free fall, which provides a practical example of uniform acceleration due to gravity, and examine related diagrams to visualize this. Throughout, we'll see how the calculus method simplifies complex motion problems, making our understanding more precise. Finally, we will tie everything together by discussing how motion is relative, meaning it depends on the observer's frame of reference, and how all these concepts interconnect to give us a complete picture of dynamics. Kinematics is essentially the study of motion, but what's important to note is that it doesn't concern itself with the causes of that motion. Instead, it focuses purely on how objects move. Today, we're going to narrow our focus to a specific type of motion called rectilinear motion, which means motion along a straight line. This is a fundamental concept because many real-world movements can be approximated or simplified to straight-line motion, making it easier to analyze. When we talk about motion in this context, we're referring to the change in an object's position over time. So, understanding how an object's position varies with time is essential to studying kinematics. This chapter will help us build a solid foundation for analyzing and predicting motion, which is crucial for many applications in physics and engineering. Let's talk about the difference between distance and displacement. Distance is a scalar quantity, which means it only has magnitude and is independent of direction. So, when you walk around a block, the total distance you cover doesn't depend on where you end up, just how far you've traveled overall. Displacement, on the other hand, is a vector quantity. That means it has both magnitude and direction. It's calculated as the final position minus the initial position, giving you a straight-line measurement from start to finish, regardless of the path taken. Now, moving on to speed and velocity. Speed, represented by v, is a scalar quantity. It tells us how fast an object is going, but it doesn't include any information about which way it's moving. Speed is always positive because it's just a measure of magnitude. Velocity, however, is a vector. It includes both speed and direction. In one-dimensional motion, we often specify the direction of velocity using a plus or minus sign. The plus sign might indicate movement in one direction, while the minus indicates movement in the opposite direction. This distinction between scalars and vectors is fundamental because it helps us understand how objects move and how to describe their motion accurately within the framework of physics. Let's talk about distance and displacement. Distance is essentially the total length of the actual path you travel from your starting point to your destination. It doesn't matter how winding or indirect the route is, it just measures the whole journey. Displacement, on the other hand, is much more straightforward. It's the length of the straight line that connects your starting point directly to your ending point. Think of it as the shortest possible path between 2 points. The key takeaway here is that distance accounts for the entire journey, while displacement focuses only on the initial and final positions, regardless of the path taken. These concepts are fundamental because they help us understand motion more clearly, especially when analyzing real-world scenarios or solving physics problems. Let's look at Rohit and Seema starting from their house. Rohit walks 2 kilometers to the east. Meanwhile, Seema walks 1 kilometer to the west, then turns back and walks 1 kilometer again. Now, notice that Seema ends up right back home. Her displacement is 0 meters. Why? Because displacement depends on the initial and final positions, not on the path taken, and in her case, her final position is the same as her starting point. This highlights an important concept. To determine displacement, you need both the distance and the direction. It's not enough to know how far someone has traveled. You also need to know in which direction they moved. For example, Rohit traveled 2 kilometers east, and Seema traveled a total distance of 2 kilometers as well, but in different directions. Now, let's consider a circular path. Imagine a boy walking from point B to point D along a semicircular arc. The distance he covers is the length of that semicircle, which is half the circumference of the circle. However, his displacement is the straight line from B to D, which is the diameter of the circle. So, when analyzing motion, always remember that distance is the total ground covered, while displacement is the shortest straight line distance from the starting point to the ending point, including its direction. An object's motion is considered uniform if, and only if its position versus time graph is a straight line. This means that when an object moves with constant speed in a straight path, the graph of its position over time will form a straight line. The slope of this graph actually represents the average velocity of the object. Speaking of units, the SI unit for velocity is meters per second, or m per s. This helps us measure how quickly an object changes its position over time. A good everyday example of uniform motion is riding steadily over level ground. When you're cycling or driving at a steady speed, your motion is uniform because your position changes at a consistent rate. To clarify what uniform motion really means, it's when equal displacements happen during equal intervals of time. So, if you move 10 meters in 1 second, you'll move another 10 meters in the next second, and so on. And of course, uniform motion always occurs along a straight line. For example, if you're driving a car at a perfect, steady 60 km/h, that means your position changes by 60 kilometers every hour. It's a clear illustration of uniform motion in everyday life. All right, let's take a closer look at this distance time graph. On the horizontal axis, we have time in seconds, and on the vertical axis, distance in meters. The graph shows how distance changes over time, which helps us understand the movement of an object. Notice how the line is relatively straight, indicating a steady increase in distance as time passes. This suggests constant speed or uniform motion. If the line were curved, it would mean acceleration or deceleration. The key point here is that the slope of the line represents the speed. A steeper slope indicates a higher speed, while a gentler slope indicates a slower speed. So, by analyzing the graph, we can tell not just how far an object has gone over time, but also how fast it was moving at different points. This kind of graph is really useful for visualizing motion, and it ties into our overall theme of understanding movement through different types of graphs. Remember, the straightness or curvature of the line gives us a lot of information about the nature of the motion. Let's take a closer look at this velocity time graph. Here, the horizontal axis represents time in seconds, from 0 to 1.25 seconds. The vertical axis shows speed in meters per second, ranging from 0 up to 50. What this graph really demonstrates is how velocity changes over time. Notice the shape of the line. It's not perfectly straight, which indicates that the object's speed is varying as time progresses. The key point here is that the slope of this line tells us about acceleration. When the line slopes upward, it means the object is speeding up. When it slopes downward, it's slowing down. A flat, horizontal line would mean constant velocity, no acceleration at all. Understanding this graph helps us see how velocity isn't just about how fast something is moving, but also how that speed changes over time. This is fundamental in analyzing motion, and it connects directly to the broader theme of understanding dynamics and how objects behave in motion. All right, let's take a closer look at this graph. Here, we see a plot of velocity versus time, which helps us understand non-uniform motion. As you can see, the time is marked along the x-axis, ranging from 0 up to about 1.25 seconds, while the velocity is on the y-axis, from 0 up to 50 meters per second. What stands out is that the velocity isn't constant, it changes over time. Sometimes it increases, sometimes it decreases, which is what we call non-uniform motion. This contrasts with uniform motion, where velocity remains steady. By analyzing this graph, we can see how the object accelerates or decelerates at different moments. For example, if the velocity is rising, the object is speeding up. If it's falling, the object is slowing down. Understanding these variations helps us grasp real-world scenarios where motion isn't perfectly uniform, like a car braking or accelerating. So the key takeaway here is that in non-uniform motion, velocity isn't constant, and observing these changes over time gives us valuable insights into the object's behavior. This concept plays a crucial role in understanding how objects move in everyday life and forms the foundation for more advanced physics topics. When an object is speeding up or slowing down, it's not moving at a constant rate, so we say it's not in uniform motion. In that case, if we look at a position versus time graph, it won't be a straight line. Instead, it will be curved or sloped differently at different points. To find the average speed between any two times, we look at the straight line that connects those 2 points on the graph. The slope of that line gives us the average speed, which is represented as VAV. Now, the instantaneous velocity is a bit different. It's the velocity of the object at a specific moment in time, at a single instant, which we denote as t. And here's an important link. As the time interval, delta t, gets smaller and smaller, the average velocity over that interval becomes a better approximation of the actual, or instantaneous, velocity. So, in essence, the smaller the time interval we consider, the more accurately we can determine the velocity at that precise moment. The instantaneous velocity at time t is essentially the slope of the line that is tangent to the position versus time graph at that exact moment. Think of it as the moment-to-moment speed of an object, not just an average over a period. In calculus, we refer to this as the derivative of s with respect to t graphically. Delta s over delta t represents the slope of a straight line, which gives us the average velocity over that interval. When delta t approaches 0, this straight line becomes tangent to the curve itself, giving us a precise measure of the velocity at that single point in time. As delta t gets smaller and smaller, the average velocity over that interval approaches a limiting value. This limiting value is what we call the instantaneous velocity at time t. In other words, the instantaneous velocity is like the average velocity during a tiny interval centered around t as that interval shrinks to 0. Now, when we look at graphs of instantaneous velocity, we're visualizing how the velocity changes at every moment. It's a powerful way to understand motion in a detailed, real-time way, connecting the calculus concept of derivatives directly to physical movement. Let's consider a function u that depends on time, specifically u equals c times t raised to the power n, where c and n are constants. Now, an important point here is that the derivative of a constant is 0. For example, if c is just a constant multiplier, its derivative disappears. Similarly, the derivative of a sum is simply the sum of the derivatives, which makes calculations more straightforward. If we have two functions, u and w, both depending on time, we can analyze their derivatives separately. The notation ds/dt represents the derivative of s with respect to t. This derivative essentially tells us the slope of the tangent line to the position versus time graph at any given moment. Understanding this slope is fundamental because it helps us grasp how quickly or slowly an object is changing its position over time. This concept of derivatives is a cornerstone of calculus and is crucial for analyzing motion and many other phenomena in physics. So, as we go further, keep in mind that derivatives give us a powerful way to quantify change in a precise mathematical manner. Let's consider a function u that depends on time, expressed as u equals c times t raised to the power n, where c and n are constants. Now, in the third step, when you see the vertical bar, that means we're evaluating the integral at the final time and subtracting the value of the integral at the initial time. This is a common way to find the accumulated change over a specific interval. Remember, the integral of a sum is just the sum of the integrals. So, if you have multiple functions, like u and w, both depending on time, you can integrate each separately and then add the results. This property makes calculations much more manageable. Now, let's talk about what taking a derivative really means. When you take the derivative of a function, you're essentially finding its slope at any given point, how quickly it's changing at that moment. On the other hand, evaluating an integral is like finding the total area under the curve of that function over a certain interval. Both operations give us vital information about the behavior of these functions over time. So, in summary, understanding these concepts of derivatives and integrals helps us analyze how quantities evolve and accumulate, which is a foundational idea in calculus and essential for our overall understanding of physical systems. The SI units of acceleration are meters per second squared, or m/s2, which you might also see written as MSS. Acceleration essentially measures how quickly or slowly an object's velocity is changing over time. To put it simply, if an object speeds up or slows down, it's experiencing acceleration. The average acceleration during a specific time interval, which we denote as delta t, can be visualized as the slope of a straight line graph showing velocity versus time. So, if you plot velocity against time and draw a straight line, the slope of that line gives you the average acceleration. Now, if the acceleration remains constant throughout that interval, then the acceleration, which we call a, is the same as the average acceleration, AAVG. It's important to remember that acceleration, just like velocity, is a vector quantity. That means it has both a magnitude, which is how much or how strong, and a direction, indicating which way the object is accelerating. Understanding these key points helps us see how objects change their motion, especially when acceleration is involved, which is a crucial part of studying motion with acceleration. All right, let's take a closer look at this graph. What we see here is velocity over time, and notice how the line is straight and steadily increasing. This indicates that the object is experiencing uniform acceleration. In other words, its velocity is increasing at a constant rate. The key point here is that when acceleration is uniform, the velocity changes linearly with time, which is exactly what this graph shows. The straight line confirms that the acceleration remains constant throughout this period. This concept is fundamental because it helps us predict the motion of objects more easily. When acceleration is uniform, we can use simple equations to determine velocity and position at any point in time. So, connecting this to the overall theme, understanding uniform acceleration allows us to analyze many real-world situations, from cars speeding up on a highway to objects falling under gravity. It's a foundational concept that simplifies the complex motion into something manageable and predictable. All right, let's take a closer look at this graph showing velocity over time. As you can see, the curve isn't a straight line, which indicates that the acceleration isn't uniform. Instead, it varies at different points in time. This concept of non-uniform acceleration is really important because, in real-world scenarios, objects don't always accelerate at a constant rate. Sometimes they speed up quickly, then slow down, or change their acceleration suddenly. Notice how the slope of the curve changes throughout the graph. This is a visual cue that the acceleration is changing. When the slope gets steeper, the object is accelerating faster. When it flattens out, the acceleration slows down or even stops. Understanding non-uniform acceleration helps us better analyze motion in more complex situations, like vehicles braking or accelerating on a hill, or objects experiencing forces that vary over time. So, connecting this to our overall theme, it's key to recognize that acceleration isn't always steady. Instead, it can be dynamic and variable, which makes the physics of motion richer and more representative of what we see in real life. All right, let's take a closer look at the key variables involved in motion. We have velocity, which is measured in meters per second, and it tells us how fast an object is moving at a given moment. Displacement, represented here as s, indicates the change in position from the starting point to the ending point. Acceleration describes how quickly the velocity changes over time. Time, t, is straightforward. It's the duration over which these changes occur. Then we have the final velocity, v, which is what the velocity ends up being after a certain period, and the initial velocity, u, which is where we start from. These variables are crucial because they form the foundation of the first equation of motion, which allows us to relate these quantities directly. This first equation of motion is fundamental in understanding how objects move under constant acceleration. It's often used to solve problems where we know some of these variables and want to find others. As we go through this, keep in mind how these pieces fit together to give us a complete picture of an object's motion. This understanding will be key as we explore more complex scenarios later on. All right, let's take a closer look at the second equation of motion. As you can see on the slide, we have key variables like velocity, displacement, acceleration, time, final velocity, and initial velocity. These are the fundamental components we use to describe motion in a straight line. When we talk about velocity, we're referring to how fast an object is moving in a specific direction, measured in meters per second. Displacement, represented by s, indicates the change in position from the starting point. Acceleration tells us how quickly that velocity is changing over time. Time, t, is simply the duration over which the motion occurs. The final velocity, v, is what the velocity becomes at the end of the time period, while the initial velocity, u, is where it started from. Now, the second equation of motion relates these variables in a very useful way. It allows us to find the final velocity when we know the initial velocity, acceleration, and displacement, without needing to know the time explicitly. This equation is really powerful because it helps us analyze motion even when the timing isn't straightforward. Remember, these concepts tie back to the overall theme of understanding how objects move and how different factors influence their motion. This equation gives us a comprehensive tool to predict and analyze movement in a variety of real-world situations. All right, let's take a closer look at the third equation of motion. On this slide, we see several key variables. Velocity, which is measured in meters per second, or ms displacement, represented as s, is the change in position. Acceleration shows how quickly the velocity is changing. Time, t, is simply the duration over which these changes happen. Final velocity, v, is where the object ends up after some time, while initial velocity, u, is where it started. The third equation of motion ties all these together. It helps us calculate one of these variables if we know the others, assuming constant acceleration. Understanding this equation is crucial because it allows us to analyze the motion of objects in a wide range of real-world situations, from vehicles accelerating on a highway to objects in free fall. Remember, the power of this equation lies in its ability to connect displacement, initial and final velocities, acceleration, and time into a single, comprehensive relationship. This makes it a fundamental tool in kinematics, helping us understand and predict how objects move under constant acceleration. Let's look at how we derive equation 1. First, note that the term a is considered constant here. This assumption simplifies our calculations and allows us to focus on the relationship between the variables. Next, we integrate both sides of the equation with respect to time. Starting from 0 up to a general time t, this step is crucial because it transforms the differential equation into an integral form, making it easier to analyze and interpret. By doing this, we effectively accumulate the effects over time, which is a common technique in calculus methods. This approach is fundamental in understanding the behavior of the system we're studying, and it ties back to the overall theme of using calculus to solve dynamic problems. Let's look at this key equation. V squared minus u squared equals 2 times a times s. This is a fundamental relationship in kinematics that connects the initial and final velocities with acceleration and displacement. Now, if we rearrange this, we can express it in terms of integrals. Specifically, the integral of u and v with respect to v, and the integral of x with respect to a. So we write, the integral from u to v of v dv equals the integral from x to some point of a dx. From that, it simplifies to v dv equals a dx. This step is crucial because it shows how velocity and acceleration relate through calculus. Next, when we integrate both sides, we essentially sum up these small changes over a period, giving us the relationship between velocity and position. And here's an important point. To demonstrate the connection between acceleration and velocity, we use the fact that A equals dv/dt. But we can also express this as dv/dx times dx/dt. This is where calculus really shines, as it allows us to switch between different variables and see how they relate dynamically. So, in summary, this slide is illustrating the calculus method for deriving the equations of motion, emphasizing how integrals help us connect acceleration, velocity, and displacement in a smooth, continuous way. When we talk about free fall, we're referring to the motion of objects that are falling solely under the influence of gravity, with no other forces acting on them. Now, an interesting and important point here is that, in the absence of air resistance, any two objects, regardless of their size or mass, will fall at the same rate. This means they will hit the ground at the same time and with the same speed. This might seem counterintuitive at first, but it's a fundamental concept in physics. The reason is that the acceleration due to gravity is constant for all objects near the Earth's surface, which we call gravity's acceleration. So, whether you drop a feather or a hammer, if there's no air resistance, they will fall together. This illustrates that in free fall, all objects experience the same acceleration, emphasizing gravity's uniform effect. This idea is central to understanding motion under gravity and helps us see how force and acceleration relate. It also connects to the broader theme of how forces influence objects and motion, which we'll explore further as we continue. Let's take a closer look at figure A, which shows the motion diagram of an object that was released from rest and falls freely. As you can see, the diagram illustrates how the object's position changes over time, with each position marked at different intervals. Since it was released from rest, the initial velocity is 0, and the object begins to accelerate downward under gravity. Moving to figure B, this shows the velocity graph of the same object. Notice that the graph is a straight line with a positive slope. This slope represents the acceleration due to gravity, which is a positive number in this case. On the surface of the Earth, that value is approximately 9.8 meters per second squared. It's important to highlight that this linear relationship indicates constant acceleration during free fall. And, of course, on other planets, the value of g would be different, affecting how objects fall there. This slide ties into the overall theme of understanding how gravity influences motion. By analyzing these diagrams and graphs, we can see clearly how objects accelerate during free fall, which is fundamental in physics. Let's take a closer look at the formula for relative velocity when two bodies are moving at an angle to each other. The equation is VAB equals the square root of VA squared plus VB squared plus 2 times VA times VB times cosine of alpha. This helps us understand how their velocities combine depending on the angle between their directions. Now, if the two bodies are moving at an angle, this is the general case, and the formula accounts for that by including the cosine of the angle. Next, when the two bodies are moving in opposite directions, the relative velocity simplifies to the difference between their speeds, so v_ab equals v_a minus. And finally, when they are moving in the same direction, parallel to each other, the relative velocity is simply the difference in their speeds as well. But it's important to keep track of the sign to understand who is faster. These different scenarios are key to understanding how objects move relative to each other in various situations, which ties back to our overall theme of motion analysis. Now let's look at what happens as the bus moves away from the tree. You see, we're comparing the position of the bus relative to the tree, which we are using as our reference point or origin. When the bus starts to move, its position relative to the tree changes. It's getting farther away. This illustrates an important concept. By choosing a reference point, we can describe the motion of an object relative to that point. In this case, the tree serves as a fixed point, and we measure how the bus's position shifts over time. This idea of relative position is fundamental in understanding motion, especially when we're analyzing how objects move in space. And it ties back to our overall theme, how we describe and understand movement by choosing different references or origins. Now, here we see that the tree appears to have moved away from the bus. This might seem a bit confusing at first, but what we're really doing here is comparing the position of the tree relative to the bus. Think of the bus as our reference point, or the origin. As the bus moves, the position of the tree changes when we look at it from this reference. So even if the tree isn't actually moving, it looks like it's shifting because our point of view is changing. This is a key idea in understanding relative motion. It's all about how we compare positions from a specific point of reference. And this concept ties directly into our overall theme of understanding motion from different perspectives. Both observations are correct. The key difference lies in what we choose as our reference point. Remember, motion is always relative. When we say that an object is moving, we're really comparing its position to another object or point of reference. So, motion isn't an absolute concept. It depends on what we're comparing it to. For example, a car might seem still relative to the road, but from the perspective of someone inside the car, they're moving relative to the surroundings. This idea that motion depends on the observer's frame of reference is fundamental in physics. That's why we say motion is always relative. When we study kinematics, we focus on describing how objects move, changes in their position over time, without necessarily worrying about what causes that motion. It's all about understanding the patterns and descriptions of movement, regardless of the causes behind it. So, in summary, whether an object is perceived as moving or stationary depends entirely on what we're comparing it to. And that's a core concept that helps us better understand the nature of motion itself.